Good morning, sir.
Good morning.
Sir, welcome back to our STC, sir.
Thank you. I'm joining from another computer system as well. I guess it will allow me to join from two, right?
Yes, sir, no issue.
Because otherwise, when the entire this PPT is on the screen and I don't see anything else, any chat or something like that. If somebody has question or something.
Yes, sir. So, good morning, everyone. So, we have our speaker of the day, Professor Virender Singh from IIT Bombay. So, he will continue his lecture from the last session he was conducted in the first day. Okay. So, it's over to you, sir. You may continue. Thank you, sir.
Thank you, sir. So I hope I'm audible. Am I audible?
Yes, sir, you are audible, sir.
Okay, so that's good. And please feel free to interrupt me on the way whenever you uh, have any question. Maybe the last presentation was more on the overview. Today we will be discussing a little bit more the details inside that, and you may need to pay a little attention. So, and feel free to interrupt me anytime. Okay, so and let me know if I'm not audible, because you never know about the internet when it stops working.
Sir, you are audible. So, no
Okay,
issue, sir. No issue.
okay. So now, first of all, I acknowledge my say collaborators on the some of the works that I would be presenting here. Professor Masahiro Fujita from Tokyo University and Professor Wolfgang Kunz from Kaiserslautern Rotten University, Germany, and DST and JST for their generous funding, and all our students who helped or who have worked on different aspects of these research. So in last presentation, we already discussed, and after that, you have gone through a series of say more detailed techniques that how we can verify the cyber physical systems, which are quite complex. And we looked at the history that the 60s 70s it was the era of mainframes. Then we migrated to the desktop kind of systems, and those were prevalent in 80s and 90s. When I was undergraduate student, I saw such kind of systems we used. And then by the end of the last century, early this century, belong to the ubiquitous computing, wherein you have multiple devices and all the devices are anyway connected to each other. And the embedded systems, they started to grow in their applications with the lot of connected sensors and actuators, I mean, ranging from say automobile to the cars to the healthcare to the airplane and all such kind of things. So now the next generation of embedded system that we discussed in the last class is a cyber physical system, where in the physical objects we are bringing into the loop rather than working separately with that physical part. So now, I mean, there are subtle characteristic of this. We discussed couple of them in the last lecture, that there is a interaction with the object. So object is always very much in loop. This is system of systems. That's very important. It's not a single system, but then here it is collection of multiple systems which are integrated to each other, and thereby the complexity is very high. And then these are the social and safety critical. Safety critical, I mean, there are so many applications. If say power grid goes down, in that case it will have impact on safety. It has impact on the society, and tremendous impact. And therefore these are very really, I mean, relevant. The airplane which is flying, and then if all of a sudden something wrong happens, and there may be unfortunately crash, then it has big impact. So now these are mostly the safety critical, or social critical as well, and therefore one has to look at this very carefully, design. And so the safety and securities are becoming more and more important, which were really no, safety was important for earlier generation embedded systems. However, the security was really not that important in last generation embedded systems. But now when everything is hooked on, the security is equally important. So, I mean, CPS challenges we discussed in the last time, that a CPS is more or less like a putting together multiple systems which can work together to do the some job. And we have seen that the large amount of effort goes in debugging and verification of the system. The implementation part is roughly like a 20%. These are the data which is coming from the avionic sector. So uh, now to almost like a 80% effort goes to debug and verification. Only 20% goes to the design implementation, and it has really big cost implication. And therefore, I mean, I have two ways. One thing is I design something and then put whole lot of effort in verifying this, or I have to design in such a way that this would be correct by construction, and I don't need to put that much effort in verifying or debugging the system. So perhaps today we will discuss some of these things, that how you can design a system which is correct by construction, or you can say verification guided design process, which makes I mean, the design more robust, and it would be say very economical, because you can tremendously cut down the cost that goes for the debug and verification. So now, I mean, we know that here today we have these mid-size or high-end cars, which are, I mean, have whole lot of like the systems which are connected to each other, and then this is a I can say the system of systems, and perfect example of embedded no sorry cyber physical system. Next generation vehicle that we discussed in the last uh, presentation as well, that we have autonomous cars, and an autonomous cars may have to ascertain that always it will maintain the safety and work correctly. So the correctness is very important, that we cannot give way. So the two things that are very important, and that some of them we discussed in the last lecture as well, that correctness of the system and composability. Composability is to handle the complexity of the large system, and correctness means it has to work correctly, otherwise here there can be a catastrophe. So that is something very important. Now correctness I can say in two ways. One is the logical correctness, and another one is the temporal correctness. Logical correctness means your system should produce the correct result, so that is the input output relationship it should maintain. It should not deviate at all from the input output relationship that was defined for a given system. But this logical correctness doesn't say anything about the time, whether the correct output would be produced after 1 second, or after produced after 1 millisecond, or produced after 1 hour, right? So so this is the only the logical correctness, that given sufficient time, whether my system is going to produce the correct output or not. The another one is the temporal correctness. That means your system should produce correct result at the right time. The time is also very important. So it's not only that a system should give me the correct result, but system should give me the result at right time. So maybe you can see that in the sequence, the logical correctness comes first. First you have to ascertain that your system is working correctly, and after that you see whether it is working correctly at right time, or it is not working correctly, say by violating the timing requirement, and thereby you can do the debug. Timing, so sometimes like the real time requirements are there, and therefore the temporal correctness is very important, that it should not delay beyond certain time. And the another thing that we also discussed last time is we want that the system should be composable. So I can take as I mentioned earlier, this is system of systems. So if I take couple of systems which are designed independently, and say verified or checked for the correctness independently, and I can integrate them together, then it should also work correctly. So therefore and therefore we can improve or enhance the productivity. So you verify each subsystems of the in isolation, and then now here at the top end, or in a hierarchical design, just you need to verify the interaction between these systems. So if you verify the interaction, it should suffice, if system is designed that way. But this is really unfortunately very hard. Main issue here is the hardware and software resources that we say share among the multiple subsystems, and if you are sharing them, then really it is very difficult when they are interacting. If they are not interacting, if they are being used by only one subsystem, in that case you can say that I can independently verify these systems, and then now if I connect them together, perhaps it should work. But if they have some say system, I mean, some components which are shared, then you cannot, I mean, you cannot argue that I mean, even when they are interacting, they will work correctly. So maybe some glimpse I want to give from our ongoing work. We have a big project, that is Indo-Japanese joint research project on architecting an intelligent, dependable cyber physical systems, targeting IoT and mobile big data analysis. So it's more on the design methodologies of the dependable cyber physical systems. Now, how to architect a big system, that's a challenge. So, what we want here is maybe I will give you a glimpse of this, and then we will discuss more about the detail inside that here, how we can do. So, one perhaps in last couple of lectures, you might have gone through the model based design methodology, etc. So if you have model, in that case here, you can synthesize or construct a system based on that model that should satisfy the model. Similar way, I mean, we are envisaging a system that is based on some kind of model, or you can say the templates. So, I mean, I have partial understanding of the system, so I can make some structure or some template. That template is formally verified by the formal techniques. Formal techniques, maybe I don't know whether you have gone through these techniques during this course. Some of these things I will discuss as I go along, like equivalence checking, model checking, or property checking, or the theorem proving. So, equivalence checking and model checking are very much used in industry. Theorem provers are not that common because those are not really, I mean, a fully automated system. They are semi automated. What does that mean is that you need some manual intervention to guide the verification process. And unfortunately, industry doesn't like anything wherein there is a human intervention. They want something, a push button solution, that the moment I push the button or press enter, this will give me the that whether my system is correct or system is incorrect. If system is not correct, in that case it should return me the counter example. So that's kind of approach generally industry uses. Therefore, the equivalence checking and theorem provers are, no, no, equivalence checking and property checking are the most commonly used tools. I'm not going into that detail, but the templates that we generate based on our knowledge, we formally verify using the formal tools. But after that, some of the part which is like here, say variable, and that part has to be automatically extracted from a given specification. So this is like the composition of the various templates in one big system, and then find out the what are the missing parts in that. So so now the automatic generation of abstracted mode of cyber physical system as the template. So we abstract that out, that is like a is kind of model. So we abstract and then make a template of that. Now what we need to do after that is we have to automatically refine these templates. See, or I'm paying attention to automatic because that is very important to design any system today. Maybe even in all my say classes, I say digital design is the easiest thing that one can do. And if you explain this to any high school student, he can do as good work as you can do. However, the problem is in complexity. Now we are not designing a system with two input variables, three input variable, four input variables. We are designing a system which has hundreds or thousands of inputs, and therefore that kind of complexity how to handle. That is the mostly the issue. So designing a very large system needs automation. We cannot do the things manually, and therefore now automatic or semi-automatic at least is needed. So we refine these templates with the simulation or emulation trace that we can get out of this. Uh, so we refine the abstracted templates by simulation or emulation, and we guarantee that it is correct through the formal methods. So it's like here the combination of simulation or emulation and formal methods. These templates are the parts of the design which is parameterized, and these parameterized parameters are like automatically extracted that here what should be there. So in last lecture I was briefly discussing that there are three ways of verifying any design. One is you can make a system correct by construction and then you don't need verification. Another one is you throw some inputs, see the output, whether output is correct or not, and then make a decision whether output is correct or not. That process is very slow, and when you can say make a sense that I can apply 1 to 10 vectors per second. So and you can compute that here for a given design how many how much time it will take to simulate large number of vectors. And therefore we are just like doing some very small say simulation for very small number of vectors. So that is something uh, very important. So but then to improve that, the invariably industry is using emulation techniques. Emulation techniques means we build these kind of hardware and software and then try to simulate that. Like for example, the hardware I can implement on FPGA, which is a reconfigurable fabric, and so um, so therefore I can accelerate that at the speed of FPGA. FPGAs are fortunately uh, operating at very high frequency, maybe about few hundred megahertz. However, the problem is that when I have a very big design that may not fit into a single FPGA. If everything fits into single FPGA, it is good. But if it doesn't fit into single FPGA, in that case, I need to divide my design. If you need to divide your design, then it comes with additional problems. And what those additional problems are, that now when I need to partition my design, and if you partition your design, in that case there are many internal signals crossing from one design to another design, and your FPGA may not support that many number of input outputs. If it cannot support that many number of input output, in that case you need to further divide the design, and therefore you may end up with having large number of FPGAs to build your significantly complex design. If I do that, then my speed is not governed by the speed of FPGA, but speed of interconnects. And now from this one, this may drop down from few hundred megahertz to something like some kilohertz or something. So that means here thousands or tens of thousands or millions of vectors I can still apply per second. So that is significantly faster than the simulation process, but the again now 3-4 order of magnitude faster, but still that cannot cover all the cases within the reasonable time, and therefore I need to select a few cases which we call as corner cases. Now those corner cases have to be verified, but it's very difficult to give a guarantee that I have say checked for all corner cases. So couple of years ago, the Intel India president Praveen Viskantaya, he said in a conference that it would be in future the industry is looking for smart validation engineers, because that is becoming the bottleneck in the industry, and they will be the highly paid people in industry, because they are they are very important to it is very important to generate these corner cases, so that you can check, as industry is heavily dependent on the simulation based or emulation based verification methodologies. The formal techniques are say coming now, but still they are not very scalable, so they cannot handle the large designs, or at least like you have a semi-formal kind of technique which is being used by the industry. So now I mean we refine these based on the simulation or emulation traces, and then we guarantee that refinement by the formal methods. So if I look at the cyber physical system has two parts. One is the cyber part, and another one is the physical part. Cyber part is like the electronic or ICT related task, wherein we have defined a system. Now this system can have software component, can have hardware component, but then the input output relationship is defined. So now I can model this entire system that is part of software hardware is by a state machine. So finite I can abstract this using a finite state machine model. The on the contrary, the physical system is say a physically moving system, and that can be defined with a say some differential equations. Sorry, on this system I don't know why the equations are not working. So this is del m by del t plus like a del m by del x plus del n by del y. This is equal to 0. Like here, this is the expression that I can define, which give the behavior of the physical system. Now this can be so what we do here is we make some template for the cyber part, we make some templates for the physical part, because physical part again you have to solve these equations, right? So and to solve these equations, maybe the differential equation have to convert it into difference equation, and then that has to be solved. So now you abstract this model, and then this model has to be refined by doing the parameter tuning. So how do you do? I'll come to that part soon. So the automatic refinement of the template based design is the crux of the problem. Now we have my say total system defined as that these are the component, and then they are interacting with each other. Some of the components are completely known to me. Some of the components may not be completely known, or partially known, or unknown. So several I may have several missing portion, like this is a missing portion. This is fixed portion that is known to me in totality in both of the physical part and the cyber part. So now the aim is to get the fill this missing portion automatically using the formal methods. So that is the real challenge or real problems that we are working on. This is like a current our ongoing work. This work with or without specification, that's another thing that we are looking at. So now the we I mean we need specification to verify that I have been given with some specification, and then I have to verify that my system is adhering to those specifications or not. However, many times the entire specification is not known to you. You may have partial specification, and then many times you feel handicapped because you cannot progress anything when you I do not have the complete specification. So now, I mean, we are looking for whether we need the full specification, or without full specification even we can work. And I'll show you that here, even without specifications, you can get your work done. The some of these things have already been done by for the hardware and software part. Now this has to be extended for various parts and the application domain. Like for example, this is one the abstraction of, say, one balloon that somebody has launched, and then now this balloon can be doing multiple things in the space, but you want that balloon should remain stable. And then now I have to tweak or change the parameter so that here it will remain stable. Then how do I do that? So now I will synthesize a program that how it can remain stable, but then those parameters, those I have to figure out that here what should be the threshold, or all those kind of things that we have to look at. So you get one input output pattern, generate the two solution which satisfy the current input output constraint. Now and then you find that uh, if you I mean within, if you give input outputs as constant, you find two solutions. One solution is good, and another solution is a bad solution, wherein it is giving the bad wrong output. And then I mean, from using that, you can figure out that here what should be the correct design. I'll come to that point using one example. So when we have formulated our problem as modeled as QBF problem, I'll come to this point, that what QBF is, how you can formulate. QBF is a quantifiable Boolean formula. Uh, so I mean, it's like a set formula wherein some quantifiers are say plugged into that. It is solved by the some sophisticated techniques like QBF solvers, or you can use the incremental set solver to do that. So I have say one template wherein I have input output relationship given with to me, and I refine this. And then once I refine this, then again I have to check, go for the formal methods, see that here for all other inputs also it can satisfy that or not. And then now if I don't find that, so I mean here I find something, so some inputs wherein it gives me the wrong output, try to say make it correct. And then like when I reach to the final solution, in that case I won't find any input wherein it gives me the wrong output, and therefore that would be the solution. So this is why how incrementally I can fill my these templates, wherein I obtain formally through mathematical procedure the values in these say missing part, or incorrect part. This also works without a specification, but I need only the simulation. That is good thing, and I'll show you why it can, because I'm just looking at the two input, wherein the two design, I mean, one design can give you some wrong, I mean, different outputs. Methods are already working with hardware and software were alone. So now maybe I'll so this is the large problem. Maybe now I'll go a little bit inside the deep inside the solution, and look at that here, how we can do this. I believe I made it clear that what is the problem, how we modeled. We modeled problem, cyber system, physical system with some templates. Those templates are formally verified, and now, but there are some missing portions in those templates. Now we have to keep on refining that until I reach to the right solution. Now, if I do like this, in that case, my verification is integrated inside the design process. I don't need to go for separate verification process for the same thing. Did I make it clear?
Yes, sir. Yes, sir. Yes, sir.
Okay, good. So now let's look at the underneath technology. How we can do that. And as I said that here, cyber physical system has two parts, cyber part and physical part, right? And within the cyber part, again we can say there is a software part, hardware part. And then within the hardware part, you have to have something. You have data path or controller controls data path, does some work, right? So this is how I'm solving that. So let's take a one example of simple digital system, because that's the kind of controller we are building, or say some logic we are building to control it. And then here this can be generalized. It will work for anything. So if I have a say function, if I represent a function with n input variables, how many different functions we can create out of it? How many functions we can create? An input and let's say one output. And this is my digital system combinational logic.
Sir, I think it's 2 power n.
2 power n. I mean 2 power n, the number of functions that we need. I mean we can represent using the n variables. So now a logic function now can be represented by a truth table. So if I have n variable, there would be 2 raised to the power n rows, right? And if I fill any value over here, if I fill any value here like a 0 1 0 1, something like that, then that would be one function. If I fill all zeros, that would be another function. If I fill all ones, in that case, that would be another function, right? So now the number of possibilities, because every row can have value 0 or 1, and therefore I can have total 2 raised to the power the number of rows. So number of rows it would be the total number of functions that we can represent. So I mean so if we can introduce 2 raised to the power n say variables, in that case we can represent any function out of it. and there are 2 raised to the power 2 raised to the power n ways to assign a value to a function. Now, I mean, this we can also do using a lookup table. And I have a lookup table with size that 2 raised to the power n. I fill any random value in that, that would be one function, and this way I can represent 2 raised to the power n function. So lookup table based design is one of the way to design any logic. Now it depends on how big lookup table you can have. Typically FPGAs do that. So if I make a lookup table, in that case, in lookup table, what is there? I have some storage element and then a multiplexer in front of that. It will choose one value based on the control input that I am getting. So now if I say that if I have two input lookup table that can have 4 entries, and output of this if I represent by a variable, say when it is 000, output is x1. Symbolically I'm writing, I'm not is defining that if it is 0 1, then output is x2. If it is 1 0, output is x3, and 1 1, then output is x4. Now if I specify the value of x1 x2 x3 x4, this will make this will give me a function, right? Now based on this input 1 and input 2, these are the select input, and it will select one of them, and then give you the output. So it can represent like two input LUT can represent all 16 possible functions. Now so this is how I can represent these functions. Now I'll give you brief about the satisfiability checking. Perhaps you might have done that before in your curriculum, undergraduate curriculum, or during this course. So satisfiability checking problem is like here a problem of sorry. So I mean, we can define this satisfiability problem as uh, as uh, so if there are three variables a, b, and c. Uh, So what I want that if this is my formula or function f, this function f, I want that here. I mean, I want a solution for this for which it evaluates to true. Then I say there exists some value of a, there exists some value of b, and there exists some value of c, such that here this formula should satisfy. So what it says, that does there exist a, b, c such that this formula is satisfied? And now in this case, this is or, this is and, right? Maybe I don't know whether you people are coming from computer science or electrical engineering. If you are from computer science, then people like to use this kind of mathematical notation. If you are from say electrical or electronics engineering, then people prefer to write a plus b, a plus b bar plus c bar dot c, like this. So this is product of some expression. every this some expression we call as clause. To satisfy this formula, every clause must be satisfied. And I want to find out the value of A, value of B, and value of C such that this formula should satisfy. My interest is to find out one pair of A, B, C that can satisfy this relationship. So to satisfy this relationship, all these clauses must be satisfied. If I say this is my clause C1, this is my clause C2, this is my clause C3. So if all clauses satisfy, in that case, this formula will satisfy. Otherwise, this won't satisfy. And one possible solution is A equal to 1, B equal to 0, and C equal to 1. Right?
Excuse me, sir. So
Yes.
I have a question, sir.
Yeah.
Sir, this is basically a three-side problem. So I think three-side problem is already proved that this is NP complete.
Yeah. Yeah. This is NP
So,
complete. Yes.
sir, I want to know that whether two-side is also NP complete or not. If yes, then why, or if no, then why?
Yeah. So two set is not NP complete.
So, sir, I want to know that why this is not NP complete.
Because two set because they like there are definite two possibilities, like inverter expression. You can write that here, if input is 1, there is no undecidability in that. See, in three set there are various possibilities, and you need to make a decision. There in two set there is no decision making. Say if I look at the inverter, if I see output, then I can figure out what would be the input. If I know input, I can tell what would be the output. But that is not the case with like a and or something like that. In simple term, I can say that way.
Okay,
If
sir.
I,
Okay, sir. I understand.
so input output relationship is completely defined from output. So that is in a way I can say that it is a reversible logic.
Yes, sir. Yes.
I have one input, one output, and then from output I can always go to the deterministic input. From input I can go to the deterministic output. But in say AND gate, if output is 0, then I don't know what was the input. If output is 1, in that case it is a deterministic relationship that input would be always 1 1, right?
Yes, sir. Yes.
But if output is 0, in that case I don't know, there are multiple solutions exist.
Yes, sir.
0 0 0 0 1 and 1 0, right?
Yes, sir.
So that makes it so in two set, if you have only the two variable, one input and one output, in that case always it is deterministic. All the clauses that you can use are deterministic. And therefore now if I know the output, I can quickly, I mean there are no changes you need to make. Say, what can be the circuit that I can make out of it? A chain of inverters, right?
Yes, sir.
That's only the possible circuit that I can make.
Yes, sir. Yes.
And chain of inverter, if I know the output, I can say comfortably, like here I can evaluate these clauses from last clause to the first clause. I will get to know that here what is my input.
Yes, sir.
Only one evaluation you need per clause. So if there are n inverters, then you need 2n evaluations.
Yes, sir. Thank you, sir. Thank you.
Right?
Thank you.
So this problem is a, I mean, as Professor Bera already mentioned, this is NP complete. So NP complete means here I cannot have a deterministic algorithm that can give me the solution within in polynomial time. Of course, if I guess, perhaps in very first attempt I can get the solution, but deterministically I may not be able to solve this problem in polynomial time. That's the problem with set. But fortunately, when the some clause is satisfiable, in that case in reasonable time we can get one of the solutions, because there can be multiple solutions. Like for example, that's what I said. If it is AND gate, and if I say output is 0, then there are multiple solutions, and one solution I can hit quickly and then it can solve. But if it is not satisfiable, in that case that is difficult. So unsatisfiability problem is more difficult problem. And sometimes we are looking for the unsatisfiability, and I'll come to that point. So but I'll go to the QBF, and will show that, because as I said that we model the problem as a QBF problem, and QBF problem is even more complex than the SAT problem. That is P space complete. Perhaps we in this lecture we don't have that much time to discuss about the complexity analysis, but one can prove that here this is a p-space complete problem. So I mean, public domain set solver that we can use can solve the problem with the millions of variables and several millions of clauses. And luckily in this century there is a tremendous development in the capacity of the set solvers. Every year there is a competition for set solver, and people are coming up with nice algorithms to make it faster. So every year you can see that here, like Moore's law, the capability of the SAT solver is also growing. See, the first algorithm for SAT solver came in 1960 by four gentlemen, and based on their name, it was named as DPLL algorithm. And then most of the algorithms were based on their some variant of that, some refinement on that DPLL algorithm. But and nothing much had happened. I mean, there would be some increment or in that until early 90s. But early 90s onwards, there was a tremendous development in SAT solver. And now, I mean, in between the community, the verification community, almost like migrated from using the SAT to the BDDs. But now, I mean, problem with BDD is that for some of the circuits it explodes intermediately, and so may not be able to handle. But in this century, the SAT has made a great or tremendous improvement, and therefore one can now its community is again shifting back towards the use of SAT. So I mean, there is a huge improvement in the performance, and then one can use. Now maybe shall we take 5 minutes break?
Yes, sir. You may take 5 minutes.
Yeah, maybe we can take, so that people can check their email or WhatsApp message. Otherwise, need to do that in between.
Yes, sir. Yes, sir. Definitely.
Yeah, shall we start?
Yes, sir. Yes, sir. Yes.
Okay, so I explained that the set problem. Now, where we can use this set problem, I believe all of you know that how you can use this in verification. See, the straightforward use of set is that if I have one design, this is my design, and this is my specification. Specification may be the function. Like, for example, I have a design of XOR gate. This is my implementation of XOR, that is not looking at the circuit. You may not say that this is XOR gate until unless you encounter. This input is X and Y, and output is, let's say, Z. And my specification is says that your Z should be X Y bar plus X bar Y, right? So this is my specification, and I want to prove that both are equivalent of each other, right? So I have to prove the equivalence. To prove the equivalence, what I can do is I take this design, take this expression. So maybe one design from this one, I can say that can make as X this one, and now this is another my design, X and Y, Z, and if I XOR this is called as miter. Now when I make XOR, then what should be the output of this? Of course, this X and X, these are connected, Y and Y are connected. So what would be the output of this? For any value of X and Y.
So, sir, if both are same, then the output will be 0. If
Yes, sir. Yes, sir. So, if both of the design are exactly identical, then output of this and output of this would be same, and therefore the output of this XOR would be always 0, right?
yes, sir.
Because
Yes. Yes.
this can give you either 0 0, or it will give you 1 1, right? There's no
Yes.
possibility of getting 0 1 and 1 0,
Yes.
Yes.
right?
Yes,
Yes.
sir.
uh, and therefore output of this must be always 0. Now if I write a set expression for this complete and want to find out whether I can get this, is there any possibility wherein I can get f equal to 1? If I can get f equal to 1, in that case here, that is the place, or that is the input for which both of the circuits are giving me two different outputs, and therefore they are not same. That means there is some bug in one of the circuits, or maybe design and specification. So my specification is assumed to be correct, then therefore there must be a bug in my design, right? So so that's how I can use set. Now getting set expression is very easy. You need to just satisfy the input output relationship. You have to express this complete circuit in terms of product of sums, and every sum is I told you is a clause, and that can be again very easily done. That how I can do that? If it is a inverter, in that case the input is A, output is B. I can generate the clause that if A is 0, this implies that here B should be equal to 1. That can give me the clause. If I say implication relationship, A implies B, this is equivalent to A bar plus B, right, from my Boolean logic. So I can write this as A plus B is one clause, but the another clause is when A equal to 1, this also implies B equal to 0. So this will give me A bar plus B bar. Now I can replace all inverters, by two clauses A plus B and A bar plus B bar. Similar way, if there is a AND gate, I can write the expression for AND gate. Input is A, B, and output is C. I know that when A equal to 1, B equal to 1, in that case here my C will evaluate to 1. This implies, now A equal to 1 and B equal to 1. That means A bar and B bar implies C. This I can say as A bar dot B bar plus C, right? And if you solve this, this will give you A plus B plus C. Oh, sorry. A into B, not A equal to 1, right? Sorry. This is A, not bar. So this will give you A bar plus B bar plus C is one clause. Like this, you can find out the other clauses, and then you just replace these clauses corresponding to every gate. Corresponding to inverter, there are two clauses. Corresponding to AND gate, OR gate, NAND gate, NOR gate, there are three clauses. Corresponding to XOR gate and XNOR gate, there are four clauses. So if you replace all these, on an average, you can get three clauses per gate, and you can find out the complete clause. So it's very easy to get it. Now, if I get it, and then I can solve those clauses for f equal to 1, in that case, normally this should not satisfy. So this is unset problem. But if it happens to satisfy, that means these designs are not equivalent, and that's where you use this. So I told you that I formulate this problem, want to solve that here. Is there any input exist that that satisfies this? Now the another problem is QBF. So this set problem that we have already discussed, that I want that this A or B and A or B bar or C bar, and C, and I want that here there exists some value of A, B, and C, so that here this can be solved. This is what we define, and this is one of the values. Now in QBF, what we define is, so here all these variables have existential quantifier, that there exist. I need one value of A and one value of B and one value of C, so that here all these clauses are satisfied. So this is existential quantifier. Like this. Now what I want to do here is, in QBF, I say there exists, I have a mixed kind of quantifier. That means there can be two quantifier. One is existential, so that means here I need one instance of that, and another is for all, that says that for all the instances of that particular variable. So I say that for there are some existential and some for all. So what it says, does there exist A such that for all the values of B there exists C such that this expression is satisfied? You got this point? There are two existential quantifiers. It says does there exist some A for which for all the values of B there exists AC, so that this expression is satisfied.
Excuse me, sir. So I have a question.
Yeah.
Sir, does this exist C comes under the scope of for all B?
All B, yes. C will come on. Yeah, all B's.
Okay. Okay. Thank you, sir.
So what it says that, does there exist any value of A such that for all the values of B there is also there exists also a C, so that this formula is satisfied. So that means here for B I am looking for the entire spectrum of B. So spectrum in this case it's a single variable, and single variable can be what? It can have 0 value and 1 value. So this so I mean theoretically I can translate this into equivalent set problem. And equivalent set problem would be that for value of B equal to 0 and B equal to 1, there should exist a value of A and C. If satisfy for the both cases, in that case here this satisfies, otherwise it won't. And how we formulate
So,
this? Yeah.
sir, this that means this exist A, that is outside the scope of for all B.
Yes.
Okay. Thank you, sir. Thank you.
So now how you can use that in debugging problem, and then that can be extended for the design problem. Now debugging problem, you have, I mean, we simulate that. So you give some, apply some input to the hardware or software, whatever you have, you will get some output. Now and we check whether the output is correct or not. Now let's say that here I get for input 1 I get the correct output. So you check, you get the output as correct output. You do this manual check or the automatic check, and I find out this some another input, second input, for which it is not the same, right? So now at least one is in error. Can I say this? I got the two instances of input. For one, output is correct. For another one, output is incorrect, right? So for second one, output is wrong. Now my debug process says that you modify hardware or software, whatever the system I have here, in such a way that output of second should also match, right? So modify hardware software so that outputs are correct even under input 2, because under input 2 I got the wrong output. So the and this input output of 2, that relationship that we are getting, that we call as a counterexample, because here for this this particular input it is giving me the wrong output. Now how I can use this in debug process? Let's say that, and I mean all of you know that this is my single bit adder. I will make a single bit adder. This is my single bit adder. All of us know that this is concatenation of two half adder, and you can get it. Now while writing maybe my VSDL or Verilog code, I made this mistake and make this as AND gate in place of XOR gate. And now I will see whether I can correct this or not. So what I do is I'll find out two set of inputs in which one is output is correct, another is wrong. So let's take that one input, all zeros. My output from the I mean this is like a specification for me. So output is 0 0. If I have apply all zeros here, in that case your output would be 0 0. Obvious. And take another input, when all ones I apply, in that case here my sum would be 1 and carry would be 1, right? That I can get out of a specification of a single bit full adder. Now if I simulate this for these two inputs, in that case I will get output for 0 0, still I will get the correct output. For 0 0, if it is 0 0, output would be 0, and then this is also 0, so this will also be 0. If 0 0, output here is 0, and then this is output is also 0, so output would be 0. So I mean, even if there is a bug here, this gives me the correct output for one input as all zeros. Keep in mind, buggy doesn't mean that here all the for every input it gives me the wrong output. If it happens like this, then the debug is or verification is the damn easy problem. But it doesn't happen. Only in some cases it gives you the wrong output. And for example, if I use a XOR gate, in this case here I replace this by AND gate. But if I replace by OR gate, in that case here OR gate and AND gate differ only in only one input. Otherwise here they are giving OR gate and XOR gate. They differ only when input is 1 1. Otherwise they are absolutely the same. So if I simulate for the next one, in that case I will get 0 1, and this is the different output from this one, and therefore I can say that this is my buggy or counter example, wherein I apply all ones as input, and then all ones the 0 1 as the output. So this is my counter example. Now okay, it's written. Now what do I do? Now my debug process should find this erroneous portion, and then it should correct that. So first find out that here which portion in this circuit is erroneous. Once I get the counter example, I have to find out that whether there is an error in this one or in this one or in this one or in this one or in this one. I have to localize that. How do I localize that? Now there are various ways of localization. If we try to debug that, so I have a specification, and like the design, I use the simulate or formal verify. Most of the time what happens, if you are simulating, in that case it passes, because I cannot apply all possible cases. However, if you use the formal verifier, in that case here you are getting for some input you are getting it failed, and then you are getting the counter examples. Now you can again simulate for those counter examples. So now my debug process is, you have to locate the bug and then you correct them. So and what I want to refine this in such a way that ultimately I won't get any counter example. If I don't get any counter example, that means my design is correct, right? So so buggy portion, I have to find out first the buggy portion, and that is my internal signal which influence the output that goes wrong. So this thing, localization of bug, we can do using the path tracing. Again, we can have this set best formulation, and then we can correct that by using a QBF kind of formulation, and I'll explain you in a minute how you can do that. So first thing is, you have to localize which portion has gone wrong. Now what do I do is, I do some simulation, and I trace these paths, that it fails in some path, it failed over here, and then if I look at that back, I do simulate. In that case I will find out that here, this is my counter example for this input 1 0 1 1 0, it failed, and then 1 1 0 is propagating like this to this output. So this is my path. I trace the path that for this input this is how it is propagating to the primary output. I take the another case, so wherein it is like again giving me the wrong output. This is another path, and now you can see that somewhere wherever it is failing here and wherever it is failing here, I can say that here these are the suspicious candidate. Now these suspicious candidates, now one has to analyze. So you, by this way you can do that. So based on the counter example, you can find this out. Suspicious person may not be accurate. I can suspect this one, I can suspect this one, I can suspect this one, but one of them may be. And now and I mean for every this one you can use the formal method to get the counter example. So now let's say how I formulate a problem. I mean, what I need to do, I mean, if I say that there is a problem over here, I have to isolate this net and see that after this person is correct or not, right? So use those suspicious candidates and then isolate them and see that whether later portion is erroneous or previous portion is erroneous. So now if I have given a specification output, and so now my output should be equal to the specification, right? That's what we want for a given specification. Output of my circuit should be equal to the specifications those are given to me. Then we look at, given an incorrect design, pick an internal signal T here, like here if you see that this portion is buggy, let's say that here I have this gate, so I pick this internal signal. Now pick this internal signal T from the design, and for the moment T is assumed to be a combinational circuit, or if it is a sequential then it is a time frame expansion. So assume that this is a total is combinational circuit. Otherwise and then I mean what you want, that my output is equal to the function of input as well as this input T, right? T because I introduced one additional variable. Earlier my output was function of only the input. Now this becomes function of input as well as T, right? So my output is function of input and T because of the wrong implementation of the T. Now so I define a design as a correctable design. So F is called as a correctable design with T if circuit becomes correct by implementing T as appropriate function of the primary input. If I can have this T as some function of the primary input, in that case I can correct this, because I can give the right input over here that can make my output correct. Therefore what I can say that my input, for all the inputs there exists some T wherein the F is, which is function of T and input, should be equal to the specification, right? Now this is equivalent, this is my QBF. If this exists, if I can find out a value of T 0 or 1, now this is equivalent that for all input, if T is equal to 0, is equal to the specification, and or sorry, for all inputs for T equal to 1, either this should satisfy or this should satisfy, right? Either T can be 0 or T can be 1.
Yes, sir.
Right? So either
Yes,
this satisfy or this satisfy. This is my pure like a formulation for say set formulation that I use when I tie this input t with permanent 0, this tie I with permanent 1, and then want to check whether my the circuit is correct with my specification or not. So for a set based debugging method, the above is true only for all a given counter example. So I can say that for all the counter example that I am getting, there exists some t such that for that particular counter example, because in counter example I am getting the wrong output, right? This also satisfies my specification. Wherein, so I want to get this solution of t,
Okay.
and my out is equal to now function of t. If I fix that t, in that case I now this t is a function now. So now we did that set based debug methodology. I can figure out that for that particular counter example, I know that what should be the value of t. Now, so now we get a set of internal signal for here, for here, for here. By modifying this portion of the circuit, entire design can become correct. And now you can generalize this methodology for a multiple counter examples. But now we may need all primary inputs for the correction, because I have to find out this t as a function of all inputs, because for that particular counter example this t should satisfy that. So maybe one way that we can use is sampling based synthesis with refinements. So what do you do is that I have you use the manual debugging process. You get a counter example. You localize the suspicious candidate, and now you generate the possible correction by this, and then again you keep doing this, and then iteratively if you keep doing, in that case you can refine this, and finally you will get the right hardware. So first you fix some suspicious portion, this portion, say this portion, and this portion, and then try to find out that what would be the solution for the next. So now you generate a possible correction for all the sampled inputs. So maybe now what I can show you, if I assume that my bug because I know that here my bug exists from this one, I localized that where my bug is, sort of I know that so if bug is there in this sub circuit only, not entire. Now if bug is there in that case, here we can fix that particular bug. So the suspicious portion we can say represent by this bug, the buggy design. Now what I can do is, so in the previous the example of adder, my XOR gate was replaced by AND gate, right? So now this was the suspicious portion. Now what do I do is, I want to find out a real, the function of this. what should be the correct function of this so that my design is correct. Now I want to find out the correct function. Now what do I do is I can replace this with a lookup table. Now lookup table is flexible. I can have any function in that. So let's say that here I replace by a lookup table and see how we can do that. So you replace the suspicious portion as a lookup table, and then you go ahead with this. So now lookup table can be represented by all I mean can represent all the logic functions of that number of input. This introduce the programmable variable inside the circuit. Now programmable variables, uh, I can have like a lookup table. If it is two input lookup table, in that case I say variable v0, v1, v2, v3. If it is a three input, in that case it has v0 to v7. If it is four variable, in that case it has four input, then it has variable v0 to v15, right? So and what uh, I want to fix the appropriate value of v0, v1, v2, v3 in such a way that my circuit should satisfy all input output relationship. So given a appropriate programming of LUT, the circuit is equivalent to the specification. That I can write as that there exists some value of these programmable variable such that for all the inputs, my function that I am writing now as function of programmable variable and input should be equal to my specification. That is function of only input. You got my point?
Yes, sir. Yes.
So I located this, say that this portion can be now replaced by I mean I want to find out the programmable variable for this, a set of programmable variable v0, v1, v2, v3, one value of that. So it says there exists some value of v0, there exists some value of v1, there exists some value of v2, and there exists some value of v3, such that for all the inputs my function evaluates to the specification. So now the problem boils down to finding out the value of v0, v1, v2, v3. Now this formulation is QBF, right? Because it has some existential quantifier and some for-all quantifier. That there exists some function for this. Some function means the value of these variables. Those are there in my lookup table, such that my function will evaluate to correct.
Yes, sir. Yes.
So now let's come back to the same problem. What did we do? We have taken so this was my erroneous portion or buggy portion, and now I put this LUT. LUT is 2 because this is 2 input gate. In that case here my LUT will have 4 variables. It will introduce x1, x2, x3, x4, and so now I have to look at find out 2 set of inputs wherein in one output is correct, another output is incorrect. So one set of input is this set 0 0 0 and this one is 0 0 0. Both are giving me the correct output. So if I feed this to this XOR gate, in that case my equivalence checker will give me output as 0. But now I have another set of input for which there is no match and my output would be equal to 1. So for this I know that output is correct. For this I know the output is wrong. Right? So what I want now, I have this input 1111 and want to find out for this particular input. Listen it carefully now. Maybe may I take 10 more minutes?
Yes, sir, definitely, sir.
So now please listen little carefully. See, this is Boolean algebra mathematics, so it needs some attention to grasp. So what I'm saying is that for this input, my output is wrong. Now I say I fix this input and go to my set solver and say that for this particular value of inputs. Now my problem was, you remember, was the for all programmable variable, for all, no, for there exists some programmable variable under which for all the inputs gives me the output same as the specification. Now I fix this input, so I'm interested only in one input. Then now this quantification is already gone because I'm interested only in one. Now I want to see that what would there exist some variable for this particular input which can give me the correct output, and correct output is coming from this circuit, right? Now if I do that, I will get to I will get this input variable 0000. If I fill this one, the lookup table of this gate with 000, in that case this will also satisfy my output for that means here I have tied up this output to logic 0, nothing more than that. But fortunately this also satisfies this one. So this satisfies this and this both. Of course it should satisfy the correct one as well. That's why I need one correct. So to satisfy correct and this incorrect both, because this should not happen that I satisfy this one incorrect one, but then it will start to unset the correct one. That's why I need two examples. One is wherein there is a equivalence, another one where there is no equivalence. You got my point? So
Yes, sir.
if I can find out, so that means if I AND the output of these two, what should be the output of these two? 0, right? If there is no counter example here, right? If there is a counter example for that particular input, in that case, now there is no error here, there is error here, so that means that it is not satisfied. So I want to find out a set, because I have now 4 variables in my circuit, no other variable. Those are x1, x2, x3, x4. x1, x2, x3, x4 are here, x1, x2, x3, x4 are here, the same variable. Want to find out the value of those variables so that my this output should satisfy. So that means that output should remain, should never become 1. So this is the current solution. That is one sample. Now, so I sampled the input. Now what do I do is, based on the now current solution, now I go other way. And other way mean that I want to find out, because for these two inputs, now it is correct, right? If I use that configuration, and this configuration is 0000, but now I say fix my configuration 0000. Can I find a counter example? Counter example means, can I find a set of input wherein both of these circuits are giving me the wrong different outputs? So I fixed this LUT value 0000, and for that that value I found the another counter example, that if A is 0, B is 1, and C is 0, then also they are giving me the wrong output. Now what I do, again I go back and say add this third instance. Keep in mind that first two instances should still remain satisfied. So I want to find out now I have three instances, 1, 2, and the third one. The third one will tell me. So I want to find, now I say I fix up the input. Here the input is 000, here input is 111, and then the third one is input is 010. And my variables are x1, x2, x3, x4. Inputs are not variable now. Inputs are fixed. And want to find out the another configuration. And that configuration is like this one, 0100. This will satisfy all three instances. So output must be equal to, when input is 000, 111, also 010. Right? So it will generate a counter configuration. So now I did this. Again, I will do this recursively. I will go to next, that, oh yeah, now for this satisfy all three. Then I will go to the next. And next one would be, I say, okay, now I fix my fix my LUT values. Here I fix my LUT values, and then try to find out whether there is any more counter example. So whether there exists any set of ABC for which output is different. So for any set of ABC where output is different. Now the configuration is 0100. So now I'm doing this for 0100, and you find some configuration. That configuration is 0110. Now again I will do the same thing. That I will go back and look at whether there is some counter example or not. So here now I will replace this with 0110 and get the another counter example. Now I won't get any counter example. Here no counter example. No counter example means there cannot exist any input for which this configuration will give you the different output from the specification. Thereby, I can say that this is my right value of that sub-circuit that I have. So this is the sub-circuit that I replaced by LUT. Now I can say, based on this, what is this? This is my XOR gate, right? If my configuration is 0110, in that case, this is my XOR gate.
Yes, sir. Yes.
And I was able to discover my XOR gate using formal way using mathematical way. Maybe nowadays somebody can say, oh yeah, I can do this using machine learning. Yes, you can also do the using machine learning, but machine learning will never give you that confidence that always it is correct. It may give you something that may be true for some simulation, but not in all cases. This here give you guarantee that in all cases this holds good. What my point?
Yes, sir. Yes.
So now maybe I so I mean these were the two circuits. I figure out that this was the gate where there was an error, and I go through the first these one counter example and one correct example. Then I added another, got some configuration. I mean here my configuration was 000. Then I got another counter example, and then now from that I got the another configuration 0100, and then I again went and then I got one more counter example, and this counter example gave me solution 0110, and now I mean I got it. Now maybe one can say that I keep on doing this for all inputs. This is tedious, but you can see this is even a small example. But I am not exploring all 8 possibilities. I only explored 4 possibilities for 4 inputs: 1, 2, 3, and 4. For four, half of them I was able to get the correct solution. So you really don't need to explore all possibilities. Within a few inputs, you can get your right function. Now I mean so I mean I can make this formulation, and that's what we have done, like a incremental set until it becomes unset, because at last it should be unset, right? It should say that here it never satisfied output equal to 1. So I keep on doing that recursively until I get unset. Once I get the unset, in that case here I can say that here there is no this thing. So you need to go through this process. Formally I can define as this one. Now I can say that my I have some input x y, sorry, uh, some input x and y. So there exists some x and y. For that here a function fxy is not equal to the specification of xy. That gives me the sad solution that here there is some value of y1 x1 in which I mean that's the counter example. Now I go for the next, and in one I'm getting the right. So I have another example. I say there exists a set of y and x in such a way that when this is not equal to 0, but at the same time from the previous counter example it should get the right value. So that means my f of y and x1 is equal to f of x1. This is my from my counter example. So x1 is should not become a counter example. That counter example should satisfy. Now I go for the third one, and I will get the another another output. So you have y is some function of x here, and x is a vector. I'm capital X when I'm writing. This is a vector. This small x1 is an instance of that vector. So for all xy, the function xy doesn't evaluate to spec as the f of I mean and f of the first instance it should satisfy, and second instance also it should satisfy, and then you get this another solution, another set of input that gives you x3 as the another instance, and this way you keep doing this one. Now you say there exists some xy which is not equal to the spec, and x y for the first instance it should satisfy, second instance it should satisfy, nth instance n minus first instance it should satisfy, and ultimately at the last here it should say that this satisfies, I mean this should not satisfy, and this satisfies, and this satisfies, and this satisfies, and this nth instance is satisfied, and if this is unset, that means I won't get any condition here. This become unset. That means whatever the configuration I have is the correct solution. That's the crux of the problem. And now you can see that in you don't need to explore all the possibilities, and this is pretty fast. So what I'm saying is that now what did we do here? We discovered the unknown function, wherein we were assuming that there is an error. So we discovered that here what is the right function that I should have. That is the configuration of LUT. And this concept we are using in our that template based synthesis, wherein some part is formally verified, some part is gray area, and that gray area is discovered like this, wherein it says that here it satisfies all the time with the say specification. So that was the main say point. Maybe there were a couple of other things, but now we do not have that much time, so we can stop over here. But I believe I have given you a sense that how I can make a template based design that is correct by construction and that is fueled by the formal methods. Now, if you have any question, please feel free to ask.
So participants, if you have any question, you may ask.
Participants who are interested in feedback link only.
Yes, yes, sir. Okay, sir. So I think that there is no question. So
I'm sorry, this is little bit mathematical, so it needs some time to grasp. But I guess I at least had given you the big picture that how I can use that using formal methods.
yes, sir. So sir, I want to thank you very much for this informative and elaborated talk, and I hope this lecture will enlighten the participants as well as the faculty members of these different universities who are present here in this virtual meet to cyber physical system as a research field. So we also hope to host you at NIT Jalandhar in near future, if you
Yes,
permit.
I look forward to come to NIT Jalandhar. I mean, I love that place. And if any participant has any question, please feel free to drop me an email. My email is listed over here.
Thank you very much, sir. Thank you very much. We'll drop an email.
So So, sir, I want to thank you for this means a nice explanation of formal verification. I want to sincerely thank you for spending your valuable time and effort for us. Thank you
I
very much.
believe that there is no repetition with the previous speakers.
No, sir, it is not a repetition. It was actually a very nice topic you have chosen for us. Thank you, sir. Thank you very much.
And it's really my honor and privilege to interact with people, and at least I have sincere request to all the participants that they should interact as much as possible. Otherwise, this offline mode, it becomes like a more boring sessions. So so please,
Yes, sir.
always do that. Okay, thank
Yes,
you
sir.
very much. It's a really great pleasure to had this interaction.
Thank you, sir. Thank you. Thank you very much.
Thank you, sir.
Disconnect.
Okay. So, thank you, participants. So, we will put the feedback link in the chat box, and the next session will be at 2 p.m. and it will be by Professor Mahesh Chandra Govil, Director of NIT Sikkim. So, please rejoin us at 2 p.m. Thank you, everyone.
Thank you, sir.
Good afternoon, sir.
गुड आफ्टरनून।
How are you?
मैं ठीक हूँ।
Okay. Good afternoon to everybody, to all the participants and Director NIT Sikkim, Professor Mahesh Govil. So now we have the speaker, and sir will continue from the where he left us in the last session yesterday. So now it's sir, over to you, sir. Thank you.
Okay, good afternoon.
Good afternoon, sir.
Okay, so Yesterday we were discussing, right, different methods for model checking and right, the various properties of when we design any system. And then I said, because of this cyber physical systems, the importance of the real-time event is increasing. And therefore, we have to be very particular, apart from the logic or the correctness of the system, about the timing properties. And ensuring the timing property is really a very difficult task, especially when the constraints are hard in nature, especially timing constraints are hard in nature. And enforcing the timing constraint is very, very difficult. And if you look around, we'll find a large set of applications which are time critical or the safety critical, or at times we define them as a real-time tasks. We discussed, right, because in the normal systems, the design is simple because you do not have the timing constraints requirements, and therefore at times the reliability is only looked at from the point of view of the hardware and the software. The time is not in picture. But when it comes to the time critical systems, yesterday I said there are large number of applications in the household also. And if you go to the more industrial automations, if you consider your factory floor, right, many applications are time bound applications. If they are not controlled in a timely manner, there might be a mesh. So we have to be very, very careful for this. Now, when we design a system, modeling is very easy. We can do the modeling, right? The correct modeling is, of course, is again a difficult task. I said we have studied so many things in the software engineering. At times, we take software engineering very easy. But believe me, when you design a system, you really need to follow all the principles which you have studied in your software engineering. Maybe the requirement gathering, right? The analysis, coding, design, interpretation, maintenance, right? And therefore, we said the simulation is one way. We can do the checking or the performance evaluation of the model which we have designed, or the system model which we have prepared. But the simulation is not always provide you the correct picture. There might be some bugs which go undetected, and later on they may lead to a failure of the system, or might be some other problems in the system. Therefore, we resort to the more mathematical methods for the verification or validation of our model which we have prepared. And therefore, we said the formal verification becomes very, very important in the modern time, right? And we have also studied that most of the system are embedded systems or the automated systems, may it be a washing machine in your house or may it be or any controlled. Nowadays we are talking about the, even then the lights are controlled through your mobile applications using sensors. But these are not the critical applications, right? If something goes wrong with the light, of course, only disadvantage is your light may not be on, right? And it's not going to affect. But we said if it is a, let's say your fire control system is and it fails when there is a fire in a house, we can understand, right, what kind of the financial loss or maybe loss of life may incur. So when we design an application, we have to ensure that it should not fail under any circumstances. Sometimes we define these kind of the design principle as the fail safe. So if your system fails, then it should be in the safe side, or it should leave your system state in a safe state. So these are some urgent requirement of any system when we design, especially the engineering paradigm. And therefore, these formal verification methods becomes very, very important. Although yesterday we have seen they are not simple to implement because of the mathematics, amount of the mathematics and the conversion of your model into the mathematical model is really difficult one. You need to have a very in-depth knowledge of the mathematical principles and or the logic. And at times all the applications of your model may not be converted into the mathematical. That is also the limitation of the present days. Okay, in the future we can think of developing more methods or automated tools where you can right, not even model automatically, but you can really verify your model which you have prepared, right? So with this, we'll continue our discussion, right? And there might be little more mathematics, which I've just put to give you some little idea. We will not be discussing in very detail because, as I said, this most of the formal verification, if it is not based on your deductive method, if it is automation for this based on the finite automata, then we have to follow all the principles which we have studied in the theory of computation or the automata theory. So now, yesterday I discussed this topic. Will we deal with this? I said there was a Pathfinder mission, and then the Pathfinder machine found itself in a problem because of some priority inversion problem. And this is, of course, is a very important aspect of your right when you deal with the critical section of the tasks, or when you talk about the task synchronization or the resource synchronization in the system, which is very important for distributed system as well, and as well as because most of the applications are now based on the cloud. So when you talk about the cloud, it's a truly a distributed system, and the task synchronization becomes very important. So we'll discuss this little late in discussion because you might find it very interesting and useful one also, and we'll see why these formal verification methods are important for that. Now we'll discuss a little bit more about this untimed temporal logic, right? So this is a logic which we put the system into the different forms of models. Your system may consist of the propositions, right? And those propositions may be in the form of your equations, or maybe form of your Boolean algebra, or maybe in the form of anything. So every statement in the design, we generally say this is a proposition, and then we say the proposition may be correct, not correct, or whatever it might be. The most important issue here is the state. State, we are well familiar with the finite state automata, where we define the states as well as the transition between those two states. So we have a set of states normally defined by sigma bar, okay, or we can say we have a state sequence. So if your system is working continuously, your state sequence can be infinite also, and then we define this is the you can say the terminology generally being used when you define some automata model of your any system, okay. And now this is something, a state sequence which you define. So state sequence can be anything depending upon the events in the system. Now we come on to the real-time temporal logic. As I said, the untimed temporal logic does not talk about the timing constraints. Okay, so therefore the finite state automata with which we are familiar, right, does not speak us about how the temporal constraints has to be satisfied. Now, when we talk about the real-time applications, all the critical systems, we have to provide the ways to mention or implement the timing constraints, which are the integral part of your any proposition or any condition or any relation in a system design. And therefore, we say temporal logic can be used to express temporally related properties about the behavior of the system. Such properties are only quantitative. It is not possible to express quantitative timing bounds on temporally related events. This is however crucial to express properties of real-time systems. Now, yesterday also, if you remember, we have discussed a little the temporal logic for the real-time systems. For real-time temporal logic, the observation have to be extended with information about their timing. This is done by representing a sequence as a timed word over state observations. So we have said there is this linear temporal logic is basically linear sequence of or the linear sequence of states observations. Okay, in the case of this, we include the time information also. So a time state sequence here we denote it by row bar. Right, in the untimed automata, your state sequence is denoted by sigma bar. So if I have to convert the untimed state automata into the timed automata, then I'll define this state as a pair of your linear sequence and bound with your timing requirement. So I is the interval here. So I capital I bar denotes the set of your time interval in which your application has to be completed. Now we know the time interval can be closed, completely closed, right, left closed, right closed, depending upon the system behavior. So a timed state sequence describes the observable propositions during an execution, including time information. Okay, so now we have a states combined with the time or the timing constraints. This is some example where it shows. Okay, now you have a state sequence here, right? So you have a empty state phi, and then you have a some, right, p proposition is present there, and right some maybe condition. Let's say your maybe your light is on or maybe your light is off or something like this, and then there is no activity. So your sequence of various events you can define, and then you can express them in the form of the propositions. What is finite state automata? I think everybody knows about this. So finite state automata is well known. The behavior of reactive system is viewed upon as continuous interaction with the environment and is best captured as non-deterministic behavior. Right? So this non-deterministic behavior is really killing for real-time systems. Right? We don't want the behavior of the system is non-deterministic anyhow, but your general purpose systems are often non-deterministic in nature, and our design is also non-deterministic. The classical finite state automation that accepts finite word is accepted, right, is adapted to accept infinite word. Such automation is called omega automation. So FSA and W automation, there is no difference. Only the difference is you have an infinite sequence of states. Okay, that's the difference only. These automata also move from state to state while accepting symbols of the input word. Since the input word never terminates, the notion of acceptance is modified. Several notions of acceptance exist. The most common one is this Bucci acceptance, right? And the infinitely often through a state that is marked as accepted. This is okay. Now we yesterday have seen the labeled transition system. So although in automation often age are labeled instead of states, this difference is not significant. Acceptance condition of the automation can be compared to fairness constraints placed upon the labeled transition systems. W automation, right? So we define fairly standard notion of W automation. To avoid confusion with other entities, we call the state of automata locations now. Okay, so states are being termed as the locations from now. And we label locations rather than transitions, and we label them with set of symbols instead of with single symbols. An automation having only single symbol in its locations can be easily obtained by splitting these locations into the single location form every symbol in the set. So this is some sort of a abbreviation, right? You can, if you want, you can expand your FSA. Okay, easy to move the labeling to the transitions. Furthermore, the acceptance conditions are slightly different and refers as the generalized Bucci acceptance. This is generalization of Bucci acceptance, but equally expressing in the sense that an automation with generalized Bucci acceptance can be converted into the normal Bucci automations. Now, this is some sort of a definition, formal definition of the omega automation. We know, right, how the FSA is being defined, and this is also 6 tuple. So your omega automation is 6 tuple. So you have a finite set of locations or the states. So L is, you can say, a set of locations or the states. Of course, we are well familiar with the finite alphabets. Then L0 is the initial state. Then Q is the transition. Okay, mapping every location with a set of symbols, right? And then we have edges, L to L, and then the final state, what should be accepted. Timed automation, as I said, okay, you have to convert the untimed automata into the timed automata, and then only difference, as I said, you have to imbibe something where you can address the timing requirements. So here we have a notion of the timer. Okay, so such words do not contain information about the time other than the discrete order of the occurrence of the symbol. Timed automata are finite state automata that accepts timed word. To do this, the automata exploit timer that can be set to a particular value and whose value decreases as time passes. Conditions on the timer can be used to enforce timing constraints. So this is just a notion that we have to assign some value to the timer, right? And omega is the transition levels, right, which you have to put on your edges, and then we say the value of the particular timer can be changed by means of the timer setting operation. So you have to define some sort of a, right, how would you going to change the timer setting. Okay, so you need a variable where timing setting is being changed. Timing conditions you have to also provide, right, how your timers can change. The timer X is an expression of one of the following form. So your timer value can be more greater than 0, right, can be less than 0, okay, and something like this. This is again a formal definition of the timed automata or timed W automata, you can say. So again, the symbols are more or less same. Only thing is, now initial state has two values. One is your L0, right? So something as in the untimed automata, but this is now combined with like this gamma 0 or nu 0, whatever it might be, but this is a time value. Okay, so timer are assigned by new 0 integer values. So now your each location is being labeled by the L0 word as well as the timing. So this is there, and then we have to play around the timing requirements of the system by mapping onto them onto the. Now he says the run describes the sequence stage automation while accepting the input, right? So when your system executes, generally we say the system is running. It should describe any moment that the location and the automation is, and what is the value of time. This can be fully described by a sequence of location, the intervals during which the automation resides in each location, and the timer value at the beginning of each such interval. So you have to define, right, the initial time, final time, what is the deadline, and so many things. So timing constraint depending upon the application has to be the part of your model or your transition diagram or your automation. This is some sort of a definition how your right run can go. So right, it can tells you how it can go from one state to another and what will happen, how you are going to modify your timing requirements. So it's more mathematical. Okay, so leave it here. Now this is an example, right, where you have a timed automata. So you can see X is a timer, right? So, and there are the two states, one is L1 and another is L2. So these are called the location, as we have said, rather than calling them the states. And then we have these edges or the transitions. Okay. So when you are in L2, right, and there is you have to generate some strings or some propositions are there which are the part of your set A, comma B. So we say this symbol A, right, when your automation is in a location L2, right, it can reside in the L2 at the most of 5 times, 5 minutes or the 5 seconds. Okay. So the value of X is greater than or equal to 0 and cannot be more than, because X, the maximum value is assigned 0. Okay. So we say X is set to 5 upon entering into L2, and it requires to remain in at least 0 as long as the run remains in the L2. Thus, a matching run cannot show symbol A more than 5 units of time without showing symbol B in between. Okay, so after 5 seconds, your transition has to go to the L1 location, right? Again, we have not put any condition for the B over there, so it can show B momentarily and then finally can come to your L2 location. So it depends upon the how you are playing with the timer and what is the condition of the timer for L1 and L2, right? The transitions can travel, okay, between the L2 and L1, and then we can see whether the propositions or the condition which we have imposed on the design can be, right, satisfied. Now, what is tabular this? So I have already said conversion of your this finite state automation to your omega automation is generally called the tabulex method. In the answer real time, we are often interested in quantitative timing properties. Instead of a state sequence of the untimed systems, we look at the timed state sequence, right? So the formulas in your LTL or timed automation, untimed automation, okay, now has to be converted to the time automation. So, right, we have said, right, event and point followed by B event, but we cannot express constraints about the timing. This we have already discussed. Now, okay, so conversion of LTL to finite state automation. To define the tabular construction real-time logic, we make use of the timer to remember the distance in time and important events in the past. Okay, so this is more or less same as the discussion which or the differences which we have dealt with the time untimed automata and the time automata. So nothing is new here, and this is some sort of a right, mathematical definition. So these are the formulas over an interval, right? 5, we have to test whether the formula or the propositions which we have provided, right, are true over the given interval or not. Okay, so your formal verification method must provide you the way to test, right, whatever the condition you are putting, okay, can be satisfied or not. And these are, to support this, we sometimes define some lemmas and some theorems. Okay, so I'm not going into detail. Okay. So finally, we say the general strategy for checking the timed state automation satisfy and given formula or its negation when they match, right, any education instance that passes through the location labeled accordingly. So it is done for a positive formula first and then the negative formula. If both are being satisfied, then we'll say our design or model is correct. Now, in the literature, the people also talk about the hybrid automation. They say the system is both continuous as well as discrete. So how to model them, right? And therefore, the automation is same. Only the difference here is your automation is extended to, right, model the events which are discrete as well as continuous in nature. So there is an example which says automobile engine whose fuel injection is continuous, but the control system is discrete. So microprocessor is a device which behaves discretely. It's not a continuous system, right? So your system becomes hybrid. Your application is continuous, but your controlling system is discrete. So what to do? Right? So it says as embedded computing becomes ubiquitous, hybrid systems are increasingly employed in safety critical applications, thus making reliability a prime concern. Rigorous reliability analysis requires formal modeling. For this purpose, hybrid automation has been proposed as a formal model for hybrid systems. We'll see just what does it mean, right? So we said it's a paradigm where mixed discrete continuous system or in a digital controller or analog plant. So discrete state of the controller is modeled by a vertices of graph. So same thing is here. We have a states which are represented by your nodes, and then you have a transitions or edges, okay, which gives you the transition. So again, the definition more or less same, but the symbol used by different authors are different. Okay, so here is we say state of the plant are the right elements of the set Rn. Okay. So the behavior of the plant depends on the state of the controller. Each control mode determines a flow condition, and each control which may cause a discrete change in the state of the plant. as determined by the jump condition. So you know, from when you move from one state to another, there has to be some condition for making the transition. Okay, so and these is some sort of way again, right? We define these. We use some set of variables to define, right, various conditions in the system, and then the okay. So some sort of description is there. Then we say we have an initial value, final value, and then the flow conditions. We can have a different kind of equations also. It says you can use the right. We call the differential equations to represent the various flows, because they are the differential equation are very useful in especially representing the system conditions in right industrial this thing. So your conditions can be in the form of the that kind of the equations also. Jump conditions of course gives you a condition where you can move from one state to the another state. Events, I think you know, right? If I say the light is on, light is off, okay. Now you are going to close the gate, or the temperature is more, something like this. So events can be the part of your this set sigma. So it's now we'll see at the example how we will apply this. So a very simple example is the temperature control. Okay, so you have a thermostat. How would you model the thermostat operation using the hybrid automata or the FSA? So we say X represents the temperature in the in your control. This temperature controller can be in off and on mode, and it says whenever your temperature is greater than or equal to 18, right? Your heater has to be put into the off mode. Okay, so the controller must switch off your this heater, and whenever the temperature is less than or equal to 22, should be in on mode. So how to make a transition, right? So we denote the flow condition X dot. Okay, so X dot is the dx upon right. It's the differential equation, very simple one. So you provide the rate of rise or the fall of the temperature. In control mode on, the heater is on, the temperature rises according to the flow condition this. Initially, the heater is off and temperature is 20 degree. According to the James condition, when X is less than 19, right, the heater may go on. Okay, because this is greater than 18. So your control remains in the off state only when you're, as we have said, whenever you are X is so transition is made whenever your right X is less than 9 days, and the heater may go on as soon as the temperature falls below 19 degree. According to this condition, X is greater than equal to 18. At the latest, the heater will go on when the temperature falls to 18 degree. So this is some sort of a representation of the how the controller for any heater can behave. Okay. Now another example is from the railway, right? How would you design a gauge controller? Okay, so everybody knows there is a crossing, there is a railway crossing, and we have a gate. So if we have to make an automatic gate, then we have to consider the design, various design. Okay, so now we will find what is the problem with the hybrid automation of the figure on the previous. This model is trained on the circular gate. The variable X represents the distance of the train from the gate. Initially, the speed of the train is 40 to 50 meter per second, right? And the distance is 1000 meter from the gate. The train issues an approach event and may slow down to 30 meter per second. At the distance of 100 meter past the gate, the train issues an exit event. The circular track is in between 2500 meter long. We write the jump condition as guarded commands, which allows us to suppress conjunction of the term this In particular, the jump condition of the control switch from near to past on this, and the jump condition is being specified like this. So you have a 3 states defined over here. So initial state is far. So when your train is far, right? So whenever its distance is 1000 or less than 1000, it issues a command to approach, and then it enters into the state near. Okay, where the speed is being also reduced by the controller, and then finally when the distance becomes 0, the gate must be closed at that time, and then when the train passes the uh, gate, then you may resort to the same kind of the speed. So speed should rise, and then the exit command should be given, and the train is again in the far state. So this is some sort of a abstraction of for the train operation. When the train is coming from the far and then reaching to the gate, and then it crosses the gate, and right. So now this is some sort of a another, again we are expanding the earlier diagram how the controller is going to behave. So controller can be in ideal state, and then depending upon the command issued to the controller, it can control a gate. So it can raise the gate, it can lower the gate, and depending upon the conditions, you have to draw this FSA. So whenever it is in ideal state, it means right, no command is being received. As soon as the command is received, right, approach command is received by the controller, the gate should be lowered. So the transition has to be made from right ideal state to the lower state, and finally, right, when the gate is being lowered and gate is closed, and when the train passes, the command exit is being the raise is being exit is being issued, and then the gate is being raised, and it goes to again ideal state because your train has crossed the gate. Now L is the lowering the gate, raise is there, and now what is a jet? So jet is nothing but jet is the time. I think this is the clock. Okay, so some sort of a clock which is associated to every state, and use a delay. How much delay is possible in a system? So your gate must be closed, must be raised within the time of right u. So clock, when the clock runs from the 0 to some value, so you should know how much time the gate is going to be closed, so that you can take the action before time. So we need a clock. So each state is being combined not only with the event, but it is being combined with the clock or the timer. Okay, so this is therefore becomes a timed automaton, right? So this is also gate automation. So it can, this shows when the gate is going to move up, when the gate is going to move down, when his gate is closed, and when the gate is open. So they are the 4 possible states only. Your gate is open, gate is closed, it's moving up and moving down. So when it is moving up, the y dot means the speed of the gate with which your gate moves up. Okay, and it should not take more than 90 seconds. So y value is being specified as a part of the state, and the total time taken by the gate to open up completely is 90 seconds. Similarly, moving down is also moving down with the same speed, right? And it takes y is greater than or equal to 0. So some conditions are being specified here. So this is more or less the same, because the automation, it only depends on how we are going to model various applications. Okay, so a lot of thought has to be given for modeling the each and every events, and therefore your design becomes more complicated as more complex systems are there. Now yesterday we were talking about, right, the digital methods also, the another branch of this where we use the theorem proving or the other aspect of the mathematical tools, and I was discussing the real-time systems where I said, right, there was a problem in the mission, and the vehicle was reset, and then finally we have to reload the another software into this, and then finally the application was completed. So this priority ceiling protocol, yesterday I said, is being designed, okay, for this thing. So we'll see that how this is important for real-time systems. Okay, so this is another application of your this formal verification, where it provides us insight why the formal verification is important, or the deductive method of verification as a part of the formal verification is important. So now it says the goal of the protocol is to prevent the formation of deadlock and the chained blocking. So now deadlock everybody knows, right? So because I have not given you here the background, so let's just go to the first slide. I can show you. So I said there is a priority inversion, okay, and here, okay. So we were talking about the Pathfinder mission 1997, where right this was stopped because of the priority inversion problem. And finally, the people realized that there is some problem in the verification process of the protocol, which was being put into the software. And then I said there is a priority inheritance protocol which was being used. And the priority inheritance protocol is having both the problems. It suffers from the deadlock and as well as the chain of blocking. So chain of blocking is nothing but, right, your particular higher priority task is going to wait indefinitely. So some sort of indeterminism in the in managing the this critical section was there. So I think everybody know what a critical section is. The critical section is where you are going to share the resources, some resources in exclusive mode. So if the resources have to be shared in the exclusive mode, then not more than one process can be there in the critical section. Now, critical section problem is a very big problem. We have studied in the operating system where we use the semaphores, right? And we have studied the monitors, we have studied the test and log, and so many techniques. But none of them are applicable for real-time systems because semaphore alone cannot work fine. It's good for non-real-time system because if you log the system and the sequence of operations of the semaphore are being controlled, then there is no problem and there is no deadlock. We did not talk about the chain of blocking. So chain of blocking, nothing but this is the duration of time for which your high priority task is going to be blocked, right? And when we say your tasks are having the hard deadline, so if this blocking duration is indefinite, you do not have a determinism in the blocking duration, then your high priority task may, right, pose to fail its deadline. If your high priority task is a critical task and fail its deadline, like yesterday we have discussed, the system can be in a disastrous mode and may result in a loss. As we have seen, your whole system was reset. Okay, nothing had happened wrong, but it could have been a task which, right? I think you remember. What was the name of this vehicle which we have launched from the India, okay, last year, and which have failed, not able to.
Chandrayaan 2, sir.
चंद्रयान, अभी क्या नाम था उसका, मैं नाम निकल के दिया. हाँ हाँ, विक्रम लैंडर. हाँ, so you know why that mission was failed. So there was some problem, right? We were not able to timely, right, start its various motors, and then finally, right, it could not land. And finally the report came, it might have landed in a different angle and might be have crashed with the surface of that. So for such applications, these kind of the software verification becomes very, very important, right? And the deadlock, as well as I said, if you have sent the timely command, but something had happened in the operating system which you are designed for the control, and then it does not operate your various elements of your system, then something is going to happen. So now what the PCP does there, now let's see how it really solves the problem, or it gives you the bounded delay or deterministic delay. So as I said in the beginning, non-deterministic design are not acceptable in real-time systems. So you have to be very, very deterministic when you say, right, that my system is going to meet the deadline or it's not going to meet the deadlines. If it is not going to meet the deadline, what can be the okay difference, and how can I address that? So I said here the underlying idea of this protocol to ensure that when a job J preempts the critical section of the another job, the execution and executes its own critical section J, the priority at which this new critical section J will execute is guaranteed to be higher than the inherited priorities of all preempted critical sections. If this condition cannot be satisfied, the job is denied entry into the critical section and suspended. The job that blocks J inherits the J's priority. Okay, so now we are talking about the some lower priority task is in the critical section, right? And okay, it blocks the high priority task. So okay. Now this is some sort of a description of a system where you have a three jobs J0, J1 and J2. Okay, now we have a two semaphores. Generally we have a one semaphore for each resource. Okay, so you have a three resources over here, right? So R1, R2, R3. Each resource is being guarded by the semaphore S0, S1 and S2. Okay, and the sequence of operation is shown here. So your job J0 needs the resource R0, which is guarded by S0. The job J1 needs the two resources R1 and R2 and being guarded by the semaphore S1, S2. The sequence of the need of your resources are also shown here. So J1 needs the R1 first and then followed by R2, while J2 needs S2 followed by S1. So this is the sequence of operation. Now we have to see whether there is a deadlock or not. Okay, and then we have to see what is going to be the problem of the chain of blocking. Now this is an example over here, right, which shows the J2 starts first. It locks J1, S2, okay, and then right executes in the critical section. Let's say this is CS2. Now while it is executing the critical section, your J1 arrives, right, and now J1 is being the high priority task. It is in the outside the critical sections, and therefore there is no problem at all. Okay, so it preempts the J2, right, and then it's start executing. But at time T2, it demands for the lock S1. What should have been done? Should be granted or not? If it is not a PCP oriented protocol, then definitely, because now your S1 is not locked. Fine. When S1 is not locked, now I'm going to grant the access to J1. Fine, and J1 may start executing the system. Now later on, when your J1 needs the S2, it will find that the S2 is locked and therefore it is being blocked, waiting for S2 to be released. Now if you see the sequence here, you see the sequence here. Now J2 needs S2 first and then S1. Now J1 has locked S1 and the J2 has locked S2. Fine, and there is a cycle. Now J2 is waiting for S1 to be released by J1, and the S1 is waiting for S2 to be released by J2, and it will result in a deadlock. So that was the scenario of the priority inheritance protocol. But in this case, what will happen? As I said, we have modified this thing and we put the priority ceiling on the protocol. And what is the priority ceiling? Each and every semaphore is being assigned the priority of the job, right? Highest priority of the job with which it is being associated. So now the priority ceiling of S1 and S2 is 1, because the highest priority job which is using the S1 and S2 is J1, right? And the priority ceiling of S0 is 0. Now the rule says whenever the job comes and it demands a resource, right? It should guarantee that the access will be given only if the priority of the job is more higher than the priority of all the locked semaphores. So here, in this case, PCP, the access to J2, J1 is denied, right, when it requests for S1, although the S1 was not locked. Okay, why it is being denied? As I said, the priority ceiling is being assigned to S1 and S2, and S1 and S2 has been used by the J1 and J2 both, and J1 being the high priority task, S1 and S2 both are having the ceiling priority 1. And when J1 comes and it requests for the access to S1, now the priority of S1 and S2 both is 1, and J1's priority is also 1. So J1's priority is not higher than the priority ceiling of S1, and therefore in this PCP the access to J1 is being denied. Okay, so we have seen that blocked by J2. Now of course J1 is having no conflict with the J1 and J2, so therefore J0 can come and then okay, execute and then go. But the question here is because there is only nested demand by J1 and J2, and finally, right, you can see the S2, then there is a nested call, so S1 is also being locked. Does it work? Unlock the S1 and S2 is unlocked. And when S2 is unlocked, J1 is being signaled and the J1 can get the access to the S2, and then finally it will go and right, do its execution, and there is no deadlock. So the problem of the deadlock which was there in the earlier protocol, priority inheritance protocol, was being solved by putting the priority ceiling on the resources or the semaphore which guards your resources. And this is the way how you are really going to resolve the problem of the deadlock. The second is okay. So let's see. How would we work to block to avoid the uh, chain of blocking? I think the example is not there, but let's assume that you have three jobs, J1, J2, and J3. Now J3 requires the S3, some protocol S3. J2 needs the protocol, the semaphore S2 or the resource S2, and J1 needs both S2 and S3. Now assume a scenario, something like this. At T0, now J3 is executing in this critical section guarded by S3. Okay. And at T1, the J2 comes and then it tries to enter into S2. As far as the semaphore PCP is concerned, right? Now, if it is a PIP, then it might be possible that the J2 will preempt the J3 because there is no conflict between the resource requirements. S2 and S3 are entirely different and there is no priority inheritance, and therefore it will preempt the J3 and start execution. Now finally at T2, when your J1 comes, right, it requests for the right, let's say S3. Okay, so when it requests for the S3, the access is being denied because your S3 is being already locked and your J1 is right blocked. Now J1 needs both S2 and S3, and therefore it has to wait for the duration of the critical section of your task J2 as well as J3. So in this case, your job J1 is going to wait at least for the duration of the CS2 plus CS3, right? If there are more scenarios here, you have a J2, you have a J4, J2, J3, and so on, and J1 requires the 3 semaphore S1, S2, S3. Then you are going to wait for the 3 critical section. And if there is more intermediate jobs, then okay. So in this way, the block of chaining is chain of block is being created, or you can say the time duration is not deterministic. So how this is going to solve? If now this is the scenario. Now if now priority ceiling which is being assigned to S2 and S3 is 1. So whenever the when J3 is executing, right, and lock the S3, J2 comes and requests for the lock at S2. Now the priority ceiling of S3 is 1 and priority of J2 is 2. So J2's priority is not higher than the J3 and therefore it is being blocked. And finally when J1 comes, it can the J3 completes its execution, and then when J1 comes, it can gain an access. So only duration of blocking is only longest duration of the critical section of one task. So this is how it guarantees the or avoids the chain of blocking also. So it becomes the deterministic in terms of the time also. Okay, so that is there. So we'll see the more interesting we are here is how the various properties of PCP are being solved. Does it based on the simulation, or does it based on the mathematical principles for proving the various properties of this thing? Okay, so this is the derivation. We are not interested in the beta this thing because we're not going to really discuss more. So lemma first says a job J is blocked by a lower priority job JL only if the priority of the job J is no higher than the higher priority ceiling of all the semaphores that are blocked by all lower priority jobs when J is initiated. So this was the fundamental definition of the priority ceiling protocol. Now I have to prove whether this is correct or not. So you can prove it using by method of induction, okay, and can prove that okay now this property of the semaphore, this property of the protocol which we have designed is correct. Okay, so now this some proof is given here. So again, not going in detail, just an idea what the formal verification means is I have put it here. Okay, sometimes these proofs are very difficult to understand, right? At times we are, because we are not reading the mathematics the way it should have been. We have read all these things like logical mathematics and then like lot more. But at times we read the mathematics just to pass and we'll get the good marks, not giving the application much importance. And therefore, when it comes when we do the research or the PhDs and other things, we find it very difficult to adopt the formal verification or deductive method for proving our results. And finally, we resort to simulation activity only, right? While we look at the good papers of the IEEE or good journals, we'll find a lot of mathematical proofs, theorems are derived, lemmas are derived, and they are being proved. Okay. And another difficulty in our India is we do not believe in teamwork. So if we can combine the mathematical guys with our research work, I think we can do these miracles also, which we are seeing in these slides. So second lemma says, suppose the critical section Jn of the job Ji is preempts the job Ji which enters in the critical section under the priority ceiling protocol. Job Ji cannot inherit a priority level which is higher than or equal to the job Ji. Okay, until job Ji completes. Okay, so this again talks about the another property of the ceiling protocol, where it says the Ji, if it is a lower priority task and it's a medium priority task comes, okay, it will not inherit the priority of Jm. Okay, it will ensure that the priority ceiling, whatever the priority ceiling to the protocol is being assigned, that is being inherited to stop the blocking by the intermediate jobs. So that is important. Again, you have to provide the proof, otherwise without proof nobody is going to believe in your theorem. Okay, so finally the proof has to be there. So therefore we have another proof over here. Then the property ceiling protocol prevents transitive blocking. I think we are aware of the transitive property of when we study the relations, right? We study the transitive relation. So A gives B, B gives C. So now, right, A gives C also. Therefore, we say if the J here it says suppose Let J3 blocks the job J2 and let the job J2 blocks the J1. So finally what will happen? The J3 blocks the J1, okay, due to the transitive property. But in case of the PCP, because we have put in the priority ceiling to each semaphore, so we prevent these transitive blocking. So your PCP is free from transitive blocking here. Okay, so this property is very important as far as to avoid the chain of blocking. If this property is not satisfied, the chain of blocking problem cannot be prevented in the system. Okay, so therefore we have derived a property for the ceiling priority protocol to avoid chain of blocking, and we have proved that there is no chain of blocking right in the system, and that too mathematical, not by simulation. Because simulation is always subjective. You might have generated some test cases which may not be applicable in some certain conditions. But here this proof is free from all kinds of the assumptions and the conditions here. Okay, so we have not made any assumption, right? So again, important one. Again, another theorem says the priority ceiling protocol is free from the deadlock. If you say it is free from deadlock, if you do not provide the sufficient proof, nobody will believe you. Okay, so again you have to give a mathematical proof, again following the principle of induction, and then you can prove that there is no deadlock in the system. So again we are using the mathematical principle to show that our protocol is right having some properties which are being proved to be correct and not subjective one. Okay, so important. Lemma 4 says let L be a job with a lower priority than the job Ji. Ji can be blocked by JL for at most duration of the one critical section, right? This beta. This is the longest critical section we define. So now a very important property as far as the determinism is concerned. So now my duration, I have designed a protocol which is deterministic as far as the timing constraint is concerned. What is determinism here as far as the timing constraint is concerned? The duration for the blocking of the high priority task by any lower priority task is equal to the greatest critical section in the system. So at least when I design system, when I do the suitability analysis, I can take this time into the consideration or this delay into the consideration while saying the deadline of the such jobs can be met or cannot be met. And therefore, this becomes very important in the suitability analysis. Okay, and therefore we are interested in the deterministic duration of the blocking of any task. But in non-real times, when you talk about the critical section, you never bother. Your process is going to be 1 hour in the critical section or 2 hours or 3 hours. Okay, it depends. But in real-time system, we are very particular. Okay, how long or how much delay the critical section is going to impose in the system, and therefore the solution has to be provided. The job J can be blocked for at most the duration of at most one element of beta. So again, it is saying right, if they are the 4 lower tasks which executes one after the another, right, and let's say your high priority task also shares all the 4 jobs. For example, I said your J3 is sharing resource R3, J2 is sharing resource R2, and let's say the another job J1 is sharing both the resources R1 and R2. In the case of PIP, I said the maximum blocking can be CS2 plus CS3, but in the PCP, it is guaranteed that the blocking can be equal to the CS2 or CS3, whichever is greater. Okay, because it depends on the scenario whether the J2 is coming first or J3 is coming first. So if your J1 is being blocked by the J2, right, the maximum delay is equal to CS2. If it is being stopped by the J3, then the maximum delay is CS3. So it depends on the scenario in the system, and therefore we say the maximum delay which is being introduced by this PCP in any system is the highest value of the critical sections in this system. Okay. And okay, so I think this gives us an idea why formal verification is important, especially for time critical systems, right? And with this, I thank you all.
Sir, good afternoon, sir.
Good afternoon.
Sir, means this question is not a part of this presentation, but sir, means from curiosity, I am just asking that suppose there is an existing algorithm, and I want to prove that my algorithm is better than the existing algorithm. So, how to do that? Means, can we do it in simulations, or do we
Yeah, I
need
think
to prove?
we all are relying on the simulation nowadays, right? As I said,
Yes,
see, when you talk about EC, they are the different. The formal methods are being used for the verification of the system, not for showing that whether your algorithm is good or not. Okay.
yes, sir.
So one is the correctness and the verification of my system. Another is the performance determination of my system. So when we talk about the performance determination, normally, right, you are comparing across the performance parameters. And normally we resort to the two things. One, simulation, of course, right? Second, if you have designed some prototype where you can show really now I have implemented the system on the actual scenario and then I have generated the results. And if we can do that, that is the best possible, and everybody believes, and your paper get published in very good journals, right? But
Yes,
at
sir.
times, because that is also difficult if you are implementing some algorithm, let's say in the existing cloud environment, I have to study the whole cloud environment and then I have to integrate my algorithm. So that's not only a time consuming, at times the resources or the access is not available, right?
Yes,
So
sir.
finally, because of the so many constraints, we resort to simulation environment only.
Okay. So,
So
if we are simulating it using some random task generation, like in real-time systems, we
yeah,
have some task sets, so we need to randomly generate some task sets. So,
yes.
in that case, is it reliable to means is it acceptable if I am doing it using simulation?
No, it is being accepted because most of the people are doing this, and that's why I said in the beginning, when we do these things, there is no guarantee that the model which you have designed for generation of the random tasks is correct or not, or it's really going to you can say map your generated task into the real scenario. And therefore, at times the people wants whether you have you used the standard data set or not. This is a question always.
Yes,
If I
sir.
use any let's say database, or if I generate my own data set, then normally the people do not rely on the results.
Yes, sir. Yes.
And therefore they say, okay, have you tested your this particular algorithm on this data set? Right?
Okay. Yes, sir.
So generating the test and reliability of test is another question here.
Okay. So, sir, can we use any benchmark for this? Means if we are relying on simulation.
Yes, as I remember, I have my one of my students working on the workflow analysis, and she used the standard data which are being provided by the people. So generally, we should use the if the standard data set is available. I think we must use the standard data sets, right? The
Okay.
people will believe, and then they rely on your results of the comparison of the various algorithms. If it is not available, then I think you have to prove the correctness of the data set also. So that is big, that becomes your duty or your part of your research, that you have to prove whatever the data set you have generated is correct and representing the real system scenario.
Yes, sir. Yes, sir.
Yeah.
Thank you, sir. Thank you. Thank you very much. Sir, so there is a question from some of the participants. So
Okay.
can we use Monte's workflow? So this is
Yeah.
from Shivendu Naik.
Yes, we have used that. Right. It can be used.
Okay. Okay. So I think he has got.
Yeah. In cloud computing environment, there are large number of data sets now available. Okay, so you can use those data sets also.
Sir, if suppose we don't have the data set, then what we have to do?
Then I said you generate your own data set and then you have to verify that your data set is correct. So there are the two possibilities. I can use some sort of standard results and try whether my results which are being generated using my data set map onto that or not. Otherwise, it's very, very difficult to say my data set is correct. Or the data set should be generated from the actual applications, right? If you say my data set is generated from the actual applications, then then it's okay.
So participants, if you have any more question, you can ask, sir. So I think there is no questions. So I want to thank you very much for this very informative and elaborate talk, sir. So I hope this lecture will enlighten the participants to choose this cyber physical system as a research field. And and
I think it's not cyber. It's your formal verification should be the chosen as a right field. And I think we should get motivated by your this this STP, as I said yesterday also. This is really becoming very, very important for researchers to come. So formal verification, learning formal verification technique, because as I said, I have also forgotten so many things, and then the Kamar said I take a challenge and then I have read from here and there. I'm not also expertise, right? Because this is really pure mathematics, and when you look at the literature, there are so many symbols and the mathematics, theorems, lemmas, and proofs.
yes, sir.
So
Yes.
at times you really struggle to understand the things, and right. So
Yes,
it's really, I think students should put more sincere efforts in learning the mathematics. Right? If they are especially the BTech students or the MTech students listening this or attending this FTP, they really have to put very hard efforts in learning mathematics. I
Yes,
think
sir.
if you have seen the IEEE papers, most of the papers you find a lot of mathematics there.
Yes, sir.
Yeah.
So actually, sir, people nowadays are moving toward the simulation-based paper. Means,
Because that is easy. See, if I do the simulation, it's very easy.
Yes, sir.
yes,
I have
sir.
embedded simulators available. मुझे तो simulator बनाना भी नहीं है आजकल. Simulator बने बनाए हैं, मिले हुए हैं, तो मुझे वो भी नहीं बनाना है. MATLAB है ना?
जी.
Yes, sir.
तो सब कुछ MATLAB में हो जाना है, आपको कुछ नहीं करना है. तो वो सिंपल है.
कर दिया
हाँ, है?
सर, पाइथन ने और इजी कर दिया.
अब पाइथन ने और इजी कर दिया है. पर पाइथन आपको फॉर्मल वेरिफिकेशन वगैरह नहीं देता ना. ये कोई भी सिस्टम आपका फॉर्मल वेरिफिकेशन थोड़ी बता रहा है. बहुत डिफिकल्ट है ना. जनरली आप देखो हार्डवेयर वाले सिस्टम तो हार्डवेयर डिजाइनर्स तो बहुत यूज करते हैं ना. दिस फॉर्मल वेरिफिकेशन मेथड्स आर बीइंग यूज्ड heavily in your this VLSI design or the circuit design and other things. We computer science guys are not very serious about this formal verification techniques. क्योंकि हमारा काम चल जा रहा है ना बिना उसके.
So, sir, there is another question from a participant. What are the latest research issues in formal verification of real-time system?
Yeah, I've seen the latest papers. Now, only issues are is because the system complexity is increasing day by day. तो automata जो theory है जिसको हमने पढ़ा था, we talk about the this finite state automata. तो उसको हम वास्तव में नए सिस्टम में कैसे लगाएं? Okay, what are the possibilities? How we can extend the theory? So I've seen some paper. अभी जैसे बताया hybrid automata एक लोगों ने कुछ propose किया है ना? कुछ लोगों ने probabilistic meta propose किया है. तो आप जाके देखोगे तो there are large number of papers which are talking about this is the same thing, right? Fundamentally same, but they are imbibing more concepts in that and in trying to apply the same concept in different systems. So a lot of work is going on, not in India but outside. There is a lot of work. So go through the literature, right, and then learn how really we can apply.
So thank you, sir. So I want to, sir, sincerely thank you for spending your valuable time and effort
Okay,
for us. Thank you, sir. Thank you very much, sir.
okay, thanks.
Thank you, sir. Uh, just a second, participant. Uh, okay, participants, and so we have a validity session at 4 p.m. and the Department of Computer Science and the director of NIT Jalandhar will be available for that one. And we hope that you will be available for that particular session also. So we are taking it positively. So right now it is 3:17, I think, and it will be started at the 4 p.m. And the feedback session of feedback link of that particular session will be available after 4 p.m. So I hope you will be available for that particular session also. So it will be 4 to 4:10, 4:15 up to. Okay. So the feedback link of this particular session will be available after 4 only. Okay. So please be with us at 4 p.m. Thank you.
So here we come to the end of this 1 week short-term course sponsored by TechCube 3 named Formal Verification of Cyber Physical Systems Opportunities and Challenges. We are highly thankful for all the authorities involved in the conduction of this STC, especially our esteemed director, sir, our head of the department, and seniors. As the validatory session, I would like to now invite our head, Professor A.L. Sangal, sir, to give the vote of thanks.
Honorable Professor Lalit Kumar Awasthi ji, Dean Research and Development, Professor Harsh, Professor Renu, all organizers, Dr. Nisha, and dear participants, a good evening to all of you from NIT Jalandhar. I'm very happy to share with you the kind of enthusiasm and the response we received from the participants across the country, and in which around 400 participants participated in this TCube 3 Technical Education Quality Improvement Program 3 of NIT Jalandhar. It was sponsored by TCube 3, and on this very important topic, that the challenges and opportunities in the formal verification of cyber physical systems. We had faculty across the globe, and I'll just brief that the first lecture was was by Professor Virender Singh from IIT Bombay, who briefed us on the foundation of the course and discussed the basics like how formal verification system is related to cyber physical system. Then we had Professor Sridhar from University of North Carolina, USA, who focused on the hybrid automata and explained a real-time problem of verifying the process of docking a satellite into ISS. Then we had Professor Parthasarthi Roo from University of Auckland, New Zealand, who focused on the formal methods for safe and secure medical devices, abstracted models, and heard on a chip design. Then we had Professor Sayan Mitra from the University of Illinois from USA, who discussed about verifying autonomous system and hybrid automata. Then we had Mr. Ramesh from General Motors USA, who discussed about the basis of cyber physical system and modeling of cyber physical system as well as the concurrent computing models. Then finally we had Professor Mahesh Chandra Govil, Director NIT Sikkim, and who is a professor, senior professor at NIT Jaipur. He discussed about the real-time system and its verification through formal methods. I, in fact, NIT Jalandhar, and especially the Department of Computer Science and Engineering, is indebted to all these international and national speakers for sparing their time and speaking on this very emerging topic. I am grateful to our Honorable Director, who had taken out time from his busy schedule and blessed us on the inaugural ceremony also, and he will bless us today also with his words of wisdom. I thank every participant and the Institute administration, Dr. S.K. Mishra, deans, and all other directly and indirectly involved with the TQ, all members of the staff for making this program a success. And special thanks to Dr. Lalatendu Bhera, Dr. Nisha Chaurasia, and Professor Harsh, and Dr. Renudhir and Dr. Geeta Sikka for taking all pains and making it a grand success. Once again, I thank our Honorable Director for motivating us and taking and encouraging us to take up such more courses. And as it is a technical education quality improvement, I think these are the various steps which have been taken, and we are exchanging this information. And I hope those who are working on these areas or those who has planned to work on these areas, this input will be of great use, very useful to them or for their research students. With these words, I thank one and all for contributing in this course and attending this course. Now over to Dr. Nisha Chaurasia for further proceedings.
Thank you, sir, for your words. So here we come to the end of this 1 week STC. Thank you everyone for being with us for all these 5 days. The feedback link for this day will be shared soon after the event ends. And I hope you will be joining us again for another event organized by the department. Take care, stay safe. Thank you everyone.
One second. I wish that the participants must speak, share their experiences, and one or two must share their experience so that wherever some room for improvement is there, because there is always a room for improvement. So they should speak out, and so that we take care of this those deficiencies, if any, uh, in future programs.
Hello, sir. Good
Yes,
evening, sir.
good evening.
I am Dr. Newlin Rajkumar from Anna University, Coimbatore, Tamil Nadu.
I see.
I have been attending this FTP in all the sessions.
Fine.
I felt that all the sessions were very informative and very useful for our research students, for our scholars and research students. All the sessions were informative and very new. The topics were research oriented. So in my personal point of view, all the topics were well organized and the sessions were very informative. So I am very thankful for as a whole the NIT Jalandhar and also the Department of Computer Science for organizing such events. This is my second event from NIT Jalandhar. I feel very happy to participate in this program and I expect more programs in the future days. So thank you very much, sir.
Thank you.
Hello.
Anybody? Yes, anybody
Hello.
else? Yes.
Good evening, sir. This is Dr. Suvendu Chandan Naik from Biju Patnaik University of Technical Education, Odisha. Actually, I remember, sir, in 2018, I tried to do this one workshop on CPSC in IIT Guwahati, but unfortunately I missed. So after my PhD, I tried to switch the area, and I found out that CPS cyber physical system is the best opportunity for doing a better research. So I would like to thank the organizing committee and all the supporting staffs of NIT Jalandhar that I attended the course, and basically the speakers from national or international, mainly the Professor Mahesh, the director of NIT Sikkim, Professor Birendra Singh, IIT Mumbai, and Shayan Mitra. All the speakers are excellent, and they enlightened lots of research issues in the CPS, and I hope that it will help me in future and also my students, so that we can carry out the more research work on this field. Again, I would like to thank you, Nisha ma'am, and a special thanks to Dr. Lalatulu Behera, who supported and who organized the event very well. I hope in future I will connect to NIT Jalandhar for more programs. Thank you all, sir.
We have another program lined up from 22nd onward. That you can see on the institute website of our department only, and I think Dr. Lalatendu, I think or Nisha want to speak something. Dr. Lalatendu. In fact, my young team has done a marvelous job in contacting the overseas speaker. Dr. Lalatendu himself is from IIT Guwahati. He has done his PhD. So there's more resources, more wisdom, collective wisdom has added to the department. And recently we have added around 10 faculty members, and all are from IITs and NITs. So it is adding to the strength of the departments. We are grateful to our honorable director for giving us this much faculty so that we can take up these new assignments.
Yes, sir.
Dr. Lalatendu,
Yes, sir. So,
anything you want to add?
so I thank all the participants to joining us, and I think we will organize more STC like this in future, and that will helpful for all the participants and also the students of our institute. So thank you everyone. Thank you.
Thank you, thank you. Thank you, everybody.
Sir, can you please send me the feedback link on chat box?
Yes, Professor Dr. Lalatendu, you kindly send the feedback link to some of the people. It's all right if one or two you have missed out of 10. It's not an issue, but you should not miss all the feedback links. All right. Thank you.
Yes, sir.
Thank you.
Sir, please provide it as soon as possible because I have another webinar.
Any overall feedback link?
It's over.
So can you send the feedback link, sir?
Any overall feedback link?
Sir, is there any overall feedback link?
No. This was session wise. This was session wise. I understand. All right.
Is there not any overall feedback link? Yes.
No. It's session wise only. We have to. If
Okay.
you want to add something, you can add in there.
Okay, sir.
Okay. Thank you.
Sir, I am not in WhatsApp group. Can you please add me?
So, what is your email?
Sir, I will send you in feedback. Yes.
You
Chat box.
send to Dr. Lalatendu. All right.
Yes, sir. Yes, sir.
Okay. He'll take care of it. Okay. Thank you. Thank you very much.